All right, welcome back to the channel and start of Unit 6, which is Differential Calculus 2. This section focuses on expanding our derivative tool belt and finding out more derivatives or derivatives of more functions in this case. So if you found the previous unit helpful, hopefully we can get into some more complex derivatives here and finish the unit with some interesting applications for you. So this is the second of our two differential calculus units. We'll call it differential calculus 2. And in this first section, 6.1, we are studying section SL 5.6 of the syllabus, finding the derivatives of some of our trig functions, exponential function e to the x, and finally our natural log function ln x. We're actually going to find some other derivatives that are not in the IB formula booklet, but you may find useful on exams and just generally interesting. So we're going to split this set of notes into a couple of different function categories, and our goal is just to explore, to begin with, what the derivatives of many of these functions that we're familiar with look like, and maybe try and guess the function that we'll find in the formula booklet for our derivatives. So we begin with trig functions, and most important thing about derivatives and trig functions is that our derivatives will only work in radian mode. So all that work we spent in a previous unit learning how to do trigonometric operation with radians, the payoff is really going to come now as all the calculus we do with trig functions only works in radians. Degrees will not work with calculus in this case. So we're going to begin with our sin x function, and we're going to explore what the derivative of that sin x function might look like. Okay, so we're going to start with a nice little graph of sin x on our TI Inspire here. So we'll graph our function sin x and radian mode, so we should see this nice kind of standing wave. And we are going to use our calculator to graph its derivative. So we can do that by selecting the little template here next to the number 9, grabbing this ddx template that we'll fill out, and then we can either feed in sin x here, just like before, or we can actually create a function dependency and feed in that first function f1 of x. Okay? So what this will do, this will graph our derivative of sin x. And at this point, you should be kind of trying to guess what this red function here could be. And if you make a prediction of cosine x, we can graph that as well. And we can see that those two functions exactly line up. Okay, so our cosine x function and our derivative of sin x, the red and the black line up. So when we return to our notes, we can write down that our derivative of sin x, given in the formula booklet, hence the red box, derivative of sin x, that's going to be cosine x for us right here. Okay. We're going to do the same thing with our cosine function. We are going to get that graphed. I'm going to turn a couple of these functions off so we don't have anything too complicated for now. So we'll go back to our f1 and we will graph our cosine x function. Okay, so we switch that to a standing cosine wave, noting the local maximum on the y-axis. Okay. And now if we use the dependency correctly, when we turn on the derivative of f1, that should update for us as well. Okay. And you may hope that this is just a simple sine function, which if we graph that in f3 with sin x, we can see that's not quite correct. So the derivative of cosine is not sine, but it is very close. To me, it looks like a sine function that's been reflected over the x-axis. So that would be negative sine x. And we see that lines up perfectly. Our red and our black curves are the same. So we can conclude that that derivative of cosine x is negative sine x. Okay? Now, you're going to miss that negative a few times. A lot of people do. So please, please, please look in the formula booklet anytime you're taking the derivative of a trig function. Both of these are given, and if we can reduce those mistakes, our problems will be easier to solve. Our final trig function is tan x. This is not really part of the IB syllabus, so not on IB exam, but never hurts to know it. Okay? If we graph ourselves our tangent function, let's get that right here. We'll graph our tan function. So here's our tan x. Looks a little crazy. Its derivative is seen here in the red. Okay, So this one is not as obvious. It's clear that tan is always an increasing function. The blue graphs are always going up. So it makes sense that the derivative is always positive. These kind of almost parabolic shaped pieces hanging out above the x-axis. This one is not obvious, so I will just tell you the derivative of tan x is a function called secant squared x, or 1 over cosine squared x. Okay, so 1 divided by cosine x squared, that will give us this function that we're seeing right here with these almost parabolic pieces. Okay? So that's just a good derivative to know. I doubt you're going to be tested on it, but if you need it, the derivative of tan x is 1 over cosine squared x, or secant x if you learned that in a previous class. Okay? So let's use these derivatives to do some problems. For us to differentiate this expression, differentiate just means find the derivative. So we will have dy dx equals 3 times 1 over cosine squared x minus 2 times the derivative of cosine x. We know that's negative sine x from our formulas in the red box. And we would simplify this down to 3 over cosine squared x plus 2 sine x. That's a nice straightforward problem to remind us how to calculate derivatives of sums or differences. Folding in a little more of the end of Unit 5 here, we're asked to find the equation of the tangent line at x equals 5 pi over 6 and give our answers in slope-intercept form and keep them exact. Okay? So we know that for a tangent line we need a point and we need a slope. We'll start work on the point part first. We know that x is 5 pi over 6. In order to get the y, we're going to have to evaluate that cosine function at 5 pi over 6. So we'll do a little trig review from our unit circle. We know that 5 pi over 6 puts us in quadrant 2. This is 5 pi over 6. That gives us a reference angle of 30 degrees. So we know the sides on our 30-degree triangle are 1, root 3, and 2. We have a negative side down the bottom because of the direction it's pointing. And then if we're asked for cosine, we could use our SOHCAHTOA. Cosine is adjacent over hypotenuse. So in this case, the adjacent side would be negative root 3, and the hypotenuse would be 2. So the value of this trig function, cosine 5 pi over 6 in radians, is negative root 3 over 2. So we can use that to complete the second half of our point. For the slope, this is where we need the derivative. So we'll find y prime. The derivative of cosine x is negative sine x. And again, we need to evaluate it at this x location of 5 pi over 6. The good news is we can use our same picture as before. So sine of 5 pi over 6, we're looking for opposite over hypotenuse. O over h in this triangle we've already drawn. So that should be 1 over 2. The negative still stays in front, so we will have a slope of negative 1/2. Now we have our point and our slope for our tangent line. We can build our equation. Our equation just involves putting these into point-slope form. So this is y minus negative root 3 over 2. We'll change that to a plus in a minute. Equals negative 1/2 x minus 5 pi over 6. We could leave it like this in case that they don't specify a form, but they do ask us for slope-intercept form. So we'll take those extra algebra steps to just clean this up a little bit with y plus root 3 over 2 minus 1/2 x plus 5 pi over 12. We can subtract our root 3 over 2 to get the y by itself, giving us kind of a complex but essentially still correct slope-intercept form. Okay, so this is our equation in slope-intercept form. Let me move it up a little bit. You can think about the negative 1/2. This is the m, and then this 5 pi over 12 minus root 3 over 2. This is your y-intercept, your b value. And they asked us for exact values, so we won't touch that or get it into any kind of decimal form. So those are our derivatives of our trig functions. Ones we really need to know are sine and cosine. If we know the tangent one as well, never hurts. Second category of function we're doing here is exponential functions. And we're going to explore this again similar to how we did with the trig functions. So we'll start with 2 to the x, okay? Exponential growth. We should be able to graph this function using a little t-table. I like 3 x values, so -1, 0, and 1. We know if we substitute in the 1, we get out 2. If we substitute in the 0, we get out 1. And if we substitute in the -1, we get 2 to the -1, which is 1/2. We can plot these 3 points on our little graph here, and we know this function features a horizontal asymptote right here at y equals 0. Okay? So we can graph our exponential growth function 2 to the x. Okay? We know it grows exponentially just like that. Okay? And our goal here is to use our calculator to see what the derivative might look like. Okay? So we'll bring that guy back in here, and we'll reproduce that graph we've just seen, our 2 to the x graph. We'll do that on a new graphing page. So y equals 2 to the x. It's pink. And we want to graph its derivative. So again, we grab that derivative template right next to the number 9. And in this case, I want to graph the derivative of, that was f4 of x. Okay? And we get this green curve. Okay? Now, what is the equation of this green curve? We'll come back to that in a minute. For now, we just want to kind of understand that the derivative of an exponential is another exponential. Okay, so I'm going to graph that green curve, just kind of freehanding it on here, knowing that the derivative of 2 to the x looks something like that. Okay. Again, what the equation is for that, I'm going to come back to in a minute. Okay. In the meantime, I'm going to graph our natural growth function, e to the x, over here. So we should know our e to the x function. E is approximately 2.718. For graphing purposes, 2.7 should be fine. We'll make our same little table of values. 1 over e, that's going to be approximately about 1/3 for graphing purposes. So we can graph that exponential growth function. Looks very similar to the 2 to the x over here. Again, with that horizontal asymptote. This is our natural growth function, e to the x. And at this point, we've studied e to the x, but we haven't really tapped into the beauty or the power of e to the x. Okay? So this is quite a special moment in our course where we get to look at the derivative of the e to the x and see something really cool. Okay? So back to our calculator, we will go ahead and change f4. I'm going to turn the derivative off so we don't spoil the magic moment. Okay? We're going to change f4 from 2 to the x. We're going to put that mathematical constant e in right here. Okay, if I can do this, so we're going to do e to the x right here. Okay. So the exponential graph changes a little bit to be our natural growth function, but watch what happens now when we turn on the derivative in green. This is the magic of natural exponential growth. It's a function whose derivative is itself. Okay? So this will likely become your new favorite function in differential calculus. It's a function whose derivative does not change when you do that derivative process. Okay? So we can graph the derivative right on top of our original function here, and we know that e to the x is also y primed. Okay? So this is given in the formula booklet. The derivative of e to the x is actually just e to the x. Okay? It's a function it's a function that does not change when you take the derivative. Backing up a little bit, if we go back to our regular exponential function 2 to the x, okay, that derivative y prime was also 2 to the x, but it was multiplied by a constant which was ln2. Okay? So this generalizes for a to the x. The derivative of a to the x is a to the x ln a. So that's that vertical stretching factor or compressing factor we saw in the first graph, where it's not exactly the same function, but it is another function of the same kind. So this is why we love e to the x, because its derivative is itself. It's the easiest derivative to take, and that will make problem solving easier when things get more complicated. So we're asked to find the gradient of this function at x equals 0. We can do that by taking the derivative. We've got a mix of exponentials and trig functions here. So f primed will be negative sine x, that's the derivative of cosine x. and then the derivative of e to the x, that just stays e to the x. Substituting in here, we get negative sine 0 plus e to the 0. If we know our trigonometry, we know sine 0 is 0, and anything to the power 0 is 1. So the gradient of this function at x equals 0 would be 1. Nice and simple. For us to differentiate this function right here, we have 3 pieces to this function in this sum. The first 2 we know how to do nice and simple, but this second piece, this 4 over x, that derivative is not as easy to do in the current form. So we will take a little prep step to prepare this for the derivative by rewriting this last term as x to the negative 1. Okay? Once it's in this form, we can differentiate all 3 pieces nice and easily. Okay? So we can find our y primed as 2e to the x plus 4 minus 4x to the negative 2, applying our power rule on those second 2 terms. I have a rule in my class that I don't allow negative exponents in the answer, so we would simply clean this up to turn that last term into negative 4 over x squared. And that would be our derivative for that one. So you can see we're mixing in all these different kinds of functions along with our previously learned power rule. All right, the last category we look at here is logarithmic functions. We can do the exploration for this one, or we can just explore the result. So for our natural log function ln x, we do have a domain restriction here, which is x is greater than 0, and the derivative of ln x will be 1 over x, again, given in the formula booklet. I would encourage you to explore this one on your calculator and make sure, but for the sake of time on these notes, I'm just going to give you that one. The derivative of a log that doesn't have a natural base, so log base a of x, again, that is very similar. That is 1 over x, but that denominator also has this factor of ln a in there as well, and you'll see that as a vertical stretch or compression if you graph it. We'll wrap this set of notes by just completing these 4 derivatives. So differentiate the following. 4 e to the x over 5. Well, we know that that can be written as 4 over 5 e to the x, and a constant multiple times a function. The derivative of that is just that constant multiple times the derivative of that function. And e to the x, our new favorite function, has its own derivative. So that derivative is just the same as the original function. Question B, we have negative 3 times the derivative of ln x, which we just wrote down as 1 over x. And we will clean this up to be negative 3 over x. So again, nice short derivatives, just using these results that are given to us in the formula booklet. Part C, we've got a longer function here. We do have an x squared inside of our log function. Now, we don't know how to take the derivative of ln x squared, so we need to get rid of that before we try and differentiate this function. We'll also rewrite the square root as a power, so we'll write that as a power 1/2, and we're going to use our log rules from a previous unit to drag that squared in front and instead write it as 6 ln x, the 6 coming from the 3 times 2 that was in the squared position. Minus 9 e to the x. Again, we haven't taken the derivative of any of these yet. This is still f of x. We can now do f primed of x, which will be 4x to the negative 1/2, just using our power rule. 8 times 1/2 is 4. Decrease the power by 1 gives us negative 1. 6 ln x will be similar to the previous example. 6 times 1 over x. And then our 9 e to the x just stays the same. Little cleanup step just to keep me happy. This is 4 over square root x plus 6 over x minus 9 e to the x. I wouldn't reach for a common denominator here. I would just leave that in that form right there. Our final one is just more power rule. So rewriting again to start. This is 4x to the negative 1/3 plus 10. That's that cube root, gives us the 1/3, and to bring it into the numerator, we need to negate the power. We can write down our derivative just using power rule, negative 4/3, x to the negative 4/3, and then the derivative of our 10 is obviously 0. Getting rid of those negative exponents just to keep me happy. Negative 4 over 3, x to the 4/3. If you want to write that in radical form, you can, but that is our last derivative in this set of notes. So just to review, we've learned derivatives of trig functions, sine, cosine, and tangent, not for the exam, but just learned it anyway. Derivatives of e to the x and a to the x, and then derivatives of natural log x and any log with a non-natural base as well. I hope you found this video useful, and I look forward to seeing you in the next one when we learn power rule.